welcome to a series of tutorials on trigonometry. This is the first tutorial. I don't know how many there'll be in this series, but probably at least 6, maybe more. It's a big topic in the Scottish National 5 curriculum, and I'm sure in the equivalent curricula around the world. I think it's often seen as quite a difficult set of topics. I hope in these tutorials that you'll see, in fact, it's quite beautiful, that nearly all the ideas are very closely related, and I can attest, as a scientist of many years, that it's extraordinarily useful. So what are we going to cover? Well, in this first tutorial, it's going to be quite basic. I'm really just going to talk about triangles. Trigonometry is a Greek word literally meaning the study or measurement of triangles. So I'll talk about triangles in this tutorial, and then in future tutorials we will introduce the trigonometric functions, sine, cosine and tangent. We'll talk about Pythagoras' theorem. We will then talk about how to calculate the area of a triangle. We'll talk about the sine rule and the cosine rule, which are very nice ways to calculate lengths and angles in triangles. We'll then talk about the functions sine and cosine and how we would draw those as graphs, and that's a bit more of an advanced topic, and I'll motivate that for you because that is often seen as quite abstract. And finally we'll talk about solving what are called trigonometric equations. These are equations where those functions sine, cosine or tangent actually appear in the equation. So that's sort of a roadmap disappearing into sort of a hazy future of the topics in this series on trigonometry, but let's start with some basic ideas. So trigonometry, I'm probably going to struggle spelling it every time. Study of triangles, and here is a triangle. What you might call a common or garden triangle. It has no special features, it's just some triangle. Now we have names for particular kinds of triangles that have some what you might call special features or symmetries. Now the most symmetric triangle we can imagine is one where all 3 lengths and all 3 angles are the same. And I've tried to draw that here, where all 3 angles are the same and all 3 lengths are the same, and we call that an equilateral triangle. And a triangle that has slightly less symmetry than this is one in which 2 lengths are the same and because of the fact that these 2 lengths are the same, by symmetry these 2 angles are also the same, and we call a triangle that has 2 angles the same isosceles. The third kind of triangle that is very important to be able to recognize and talk about is a triangle where 2 of the lines meet at a right angle. There is such a triangle, and when we have 2 lines meeting at a right angle, we have a special symbol for that angle. We don't draw it as a sort of a curve for the angle, but we draw a little square there to just indicate that that is a right angle, and we call this a right-angled triangle or a right-angled triangle. Okay, and we often just draw a little triangle to mean the word triangle. So equilateral triangle, isosceles triangle, right angle triangle. Now, a very important fact is that the internal angles of any triangle add to 180 degrees, which you can write as 180, and then this little sort of bubble floating up this little circle means degrees. So the internal angles we mean in this common or garden triangle that I drew, that is not privileged to be in one of these more fancy classes, it's just a common or garden triangle. These three angles will guaranteed add up to 180 degrees. And that's a very important and useful rule about triangles. Immediately it tells you that in the equilateral triangle, because all three angles are the same, it must be that each angle is 180 degrees divided by 3, which is 60 degrees. So in an equilateral triangle, each angle is 60 degrees. Now, in a right angle triangle, this right angle, by definition, is 90 degrees, and therefore it must be that the other two angles add to 90 degrees, and that's a very useful and important thing always to remember. If you have a right angle triangle, the two angles which are not the right angle must add to 90 degrees, because all three angles must add to 180 degrees. Now, I think what I'm going to do in the rest of this introductory tutorial is actually just speak about this statement. I could just state internal angles of a triangle add up to 180 degrees and move on, but it's this kind of thing which can, for many people, seem quite vague, and it's this sort of thing that can turn people away from maths because they just feel they've been given some rather vague statement and they feel they have nothing to hold on to. So let me just speak briefly about what a degree is, and let me just motivate for you why it is that for any triangle the internal angles add up to 180 degrees. And to do this, we actually have to start with a circle. Not the easiest thing to sketch. There's a relatively good circle, it's not too bad. Now, by definition, we say that a circle is 360 degrees. So this actually defines what we mean by degrees. And you might say, well, why 360? And that is lost in the mists of time. It may be due to a very ancient civilization called the Babylonian civilization, which was quite advanced in astronomy and geometry. And they loved the number 60 because the number 60 has many other numbers that you can divide into it. So 1, 2, 3, 4, 5, 6, and 12 all divide into 60. And so for an ancient civilization, that was a great number to sort of use as a guide, because you could do arithmetic very easily because many numbers divide into it. So possibly the Babylonians liked the equilateral triangle, and they therefore called that 60 degrees, and thereby the circle had 360 degrees. Why these are connected we'll now see. But in any case, in modern times, we define the degree by being that unit of angles such that 360 of them are a full rotation on a page in a plane, 360 degrees. So let me use this. If you just accept from me that a circle has 360 degrees, let's use that to argue that any triangle has internal angles that add up to 180 degrees. So let me draw sort of a crosshairs through this, make it look like something you might see through a gun. And by drawing these two lines at right angles through the center of the circle, we see that we have 4 right angles. So this already tells us that a right angle, by which we mean the angle between two perpendicular lines, is 90 degrees, because 4 of them fit into a circle. So a right angle is 90 degrees. That means that if I draw a rectangle, any rectangle, again by definition a rectangle is a shape with 4 sides where each angle is 90 degrees, then we know for this rectangle that the internal angles of a rectangle must add up to 4 times 90. So for a rectangle, the internal angles sum to 360 degrees because we have 4 right angles. And now let's imagine I sort of pushed on the top of this rectangle and skewed it, but I kept the length of the sides the same, so it's the same rectangle. I just pushed and skewed it. Then my 4 right angles have disappeared, but we can argue quite easily that I still have angles inside here that sum to 360 degrees. This shape is called a parallelogram, and the internal angles still add to 360 degrees. Let's see why that's true. One way to think about it is that the degree to which this angle gets smaller is exactly the degree to which this angle gets larger, and so these two must continue to add up to these 2 right angles, 180 degrees. We can do it a bit better than that if we just continue these 2 lines here. These 2 lines are parallel, and therefore this angle here will be the same as this angle because it's just a Z shape, and this angle will be the same as this angle. Okay, so I can maybe indicate with a dot that those 2 angles are the same, and with a cross that these 2 angles are the same. But you see now that these 2 angles must add up to 180 degrees because they lie on a straight line. You see, a straight line has 2 right angles. A straight line has an angle of 180 degrees. So these 2 must add up to 180. So these 2 add up to 180, and therefore, given that these 2 angles are just the same, then the internal angles add up to 360. And now we're done, because if you are happy that the internal angles of a parallelogram add up to 360 degrees, I can make an arbitrary triangle now by just cutting through as a diagonal there, and I just have some triangle here, or I could have gone through the other way. And now for this triangle, by symmetry it exactly cuts this parallelogram in half, and so its angles for this shape must add up to half of 360. So the internal angles of this triangle add to half of 360, which is 180 degrees. So what we've used here is the fact that there are 360 degrees in a circle by definition. We then use that to say that a right angle has 90 degrees. We then looked at a rectangle, pushed it into a parallelogram, cut the parallelogram in half to get a common or garden triangle, and argued by symmetry all the way through, therefore, that the internal angles of a triangle add to 180. So this is a very helpful and important statement to always bear in mind for triangles. It helps you find any angle. If you know 2 angles, you can always get the third angle because they have to add up to 180 degrees. As I say, for a right angle triangle, you know that the 2 angles which are not the right angle add up to 90 degrees. And hopefully this has demystified a little bit for you why we talk about 180 degrees for the internal angles of a triangle. So in the next tutorial, I'm going to look at a right-angled triangle. I'm going to talk about Pythagoras' theorem, and I'm going to define for you some very important functions, the sine, the cosine, and the tangent. So I'll see you then, and thank you very much for your attention.